Okay. So, of Euclidean transformations, I've talked about the translation, and I've talked about reflection in a line. So, as promised, I continue my program of presenting you a special case of Euclidean transformations and giving what I consider to be the most typical applications. Okay, so now I would like to talk about another very well-known transformation. It's rotation. So the expression is the rotation about rotation. So two data are required to define a rotation. One, a point, and another is angle. So rotation about a point, you say P. So this is the center which the rotation fixes, and about P. And you say through angle, through the angle theta. Okay, so theta is a real number modulo 2 pi. So this is an element of the additive group R by 2 pi z. So theta, the angle, we consider to be just a real number, and we consider two such real numbers to be the same if they differ by an integer multiple of 2 pi. Okay, so the rotation about the point P, so center of rotation, is a map. So let me make use once again of the vector space structure of R2. So what this does is that okay. So let me first give it a picture. So that's the point P. For every point X, which does not coincide with P, the rotation leaves the point P, and every point X, which does not coincide with P, undergoes a transformation in such a way that, okay, so X moves into the point X prime, okay, so that Px is equal to Px prime, and X prime is angle theta. So let me make my situation precise by giving you the analytic expression. So it means that you are actually sending the vector Px into the vector Px prime. So exactly what's happening is that the point X is, of course, when you take the point P. Okay, so X goes into, let me use vector notation. So the point P, the center of the rotation, is fixed, and X itself can be expressed by saying that this is, of course, X. Now, if I rotate this vector by angle theta. Now, what's this? This is the matrix, so I'm writing it in vector notation. So this E theta is, in fact, E theta is simply the 2 by 2 matrix, which is this. Have I got this right? I wonder. Well, to check if this is correct, all you have to do is to notice that when you apply this matrix to this simple unit vector, it goes to point. Yeah, that's right. Okay. So there it is. That's what the rotation about P through angle theta does. Okay. So perhaps right. So that's the definition. And of course, you know, intuitively the situation is clear. Allow me to show you how to use the rotation in solving problems in Euclidean geometry. Well, the examples which I shall present, I don't know, you may or you may not like them in the sense that perhaps you won't feel the need to apply rotation. You can see the thing yourself. So just, well, it's up to you. So the problem sheet contains a number of problems which can be solved more easily by using rotation. Or, I mean, you might like to think of the concept of rotation as an instrument to amplify your intuition. Okay, here's typical, I think, what you might call the amplify intuition situation. It is, okay, so it's the, so application, let's say. Now this is a very simple elementary result, yet I think the fourth application, I'm not quite sure how many applications I gave you. Okay, so this is about a triangle, and this is about an equilateral triangle, and it's circumcircle. Well, the result is rather surprising. I mean, personally, when I first learned it, I was rather surprised. So equilateral triangle. Now that is not my forte. I personally dislike the thing intensely, really, but you know, occasionally you may just have to. Okay, so this, I think, is more or less an equilateral triangle. Right, so let's call this equilateral triangle ABC. Now, here is the surprising result. That if you take a point P, let's say on the arc BC, which is not on the same side of the line BC as A. So let's take a point something. Okay, here is this on the circumference. Well, the surprising result is the following. The length of the line segment PA is actually the sum of the now here is the surprising result. The sum of the lengths of the line segment PC and the line segment BP. Okay. I rather find, I don't know. I mean, it's a matter of personality, perhaps, but to me, this is rather unexpected. So the result, okay, so you might like to consider this as a classical problem. Prove. So let me note, ABC is isosceles, equilateral. So it's a very special kind of triangle, equilateral, and prove that the length AP, shall I write it? Okay, let me write it like this. PA, the length PA, is in fact exactly the sum of PB and PC. Okay. Now let me make it clear once again that this sort of thing happens only if you take the point P on the arc, which joins B and C and is not the one that contains A. Okay. So the line BC separates the circumcircle of the triangle ABC into two arcs. One is the arc that contains A, the other that doesn't. Okay, so P is on the arc that doesn't. Okay, so this is an inequality. I shall revisit this equality. In fact, this is the special case of a very famous theorem. Okay, so let me make a note. Okay, so this may be obtained. This may also be obtained. As a simple application, as a very simple application. As a very simple application of Ptolemy's theorem. Ptolemy's. And I shall do it next week. Ptolemy's theorem. But that comes later. Okay? So, using rotations, how can you do it? Well, using rotations, perhaps the best thing to do, to observe in the first place that, so this angle is 60 degrees, because it's an equilateral triangle. Well, since, just a minute. Well, it means that this too is 60 degrees. Well, I'm not quite sure if I have been quite successful in. Never mind. Okay, so that's 60 degrees. So it means that. For instance, let me do it like this. If I take a point on the line segment, PA, which has got the same length as PB. Okay, so let me call this point Q. Well then, so that these two have the same length, and this is 60 degrees. It means that if you join QB, then you have got this QBP must be equilateral. Okay, so şöyle yapalım. Let PQ be the same as PB. Then it follows that QBP is equilateral. Well, lateral. Okay. Well, what can we say? That's the rest is quite easy. You see, So it means, so I can, for instance, let me. So this is green. Okay. This actually finishes it, because you see, I'm afraid I have not. So actually, this is not a very good equilateral triangle, and that's the whole trouble. I really want to give you a good picture. Just have some patience with me. So I think this should be more like it. But this is more like an equilateral triangle. That's B. Okay, so this slight correction. So here we are. Right. That's my point Q. Okay, so the same thing. So I've got this equilateral triangle. Fine. Now there is, okay, so it means that BP and QP are congruent. Not only that, of course, QP is also congruent. So this tells, there is one thing, you might like to proceed like this. You might like to say, well, you see, So this angle is also 60 degrees. So is this angle 60 degrees, because the triangle ABC is equilateral. We have found that QBP is also equilateral. So it means that this angle and this angle must be equal. That's how you may argue, how you might argue. And then you have got two interesting triangles. Let me show you. The one triangle is BCP, and the other triangle is BAQ. Do you see? These two triangles are the same, must be the same, because this angle and this angle are equal. 1 and 2 are equal. The sides BP and BQ are equal. The sides BC and BA are equal. So it follows that the line segment PC is the same as the line segment AQ. Okay? So your proof is very simple. The proof simply is that, so if you want to have the length PA, well then you can consider it to be the sum of PQ and QA. But then we have shown that, we have in fact chosen PQ to be the same as PB. And QA has turned out to be exactly the same as PC. So that there you are, finished. Şimdi çocuklar, you can, okay, so that, as you can see, I have not made use of the concept of rotation. In fact, you don't have to use the concept of rotation, but observe the way in which the concept of rotation may really help you to realize the situation. So if you take, for instance, if you imagine a rotation with center at B through the angle pi over 3 being your 60 degrees, you see that rotation actually takes BP into BQ, doesn't it? And for BC into BA, you know. So that's the very same rotation. That's the very same rotation. Okay, so let me call this phi if you wish. And this is phi. So is this phi. Okay, so it means that this rotation in fact takes the triangle BPC into the triangle BQA. So that, I think that's a lot of help intuitively. So you're actually rotating one triangle, and to make it so that when you rotate it through 60 degrees, it actually, you can see it, it's visible now, that one triangle coincides with the other triangle. Of course, you can argue this blow by blow argument you can give to show that the triangle BPC and the triangle BQA are in fact congruent. But this is, I think, a lot of help intuitively. You actually see things rotate and actually coincide with something else, which is a lot of help. Okay, actually, I shall be giving you instances of the situations where you can actually use rotation in a vital fashion, but this was, so to speak, a secondary way of using rotation as a help to intuition. Okay, now I would like to give you yet another application, and in that application too, okay, so this is the fifth application, I guess. In this application too, the rotation will be used, well, not as a primary, as an indispensable instrument, but more as an aid to your intuition. This is actually a rather, this second one is a rather famous problem. It is, I think, being referred to as the Pharma Torricelli problem. And in fact, it can be argued that this kind of problem is practically important too. So it's the following. Let's say you've got a triangle. Now I shall need some space. Suppose you've got a triangle like this, ABC. There is actually in my mind a certain restriction about this triangle, but I will tell you later. Okay, so that's your triangle, A, B, C. Now the question that, in fact, Pharma, Pierre de Pharma, well, as usual, proposed the problem, and the solution came from Torricelli. Torricelli was the young and ingenious student of Galileo himself. Galileo appears to have no success with the problem. Galileo tried to solve the problem, but he couldn't solve it. Okay, and Torricelli, of course, the name Torricelli, Evangelista Torricelli, should be known to you. He's famous for, having made this very famous experiment with mercury. The column of mercury with height, altitudes 76.5 centimeters. Okay, and that corresponding to the weight of the air column inside the atmosphere, so that he actually proved that air exerted pressure on everything. And it was not discernible to human faculties just because it acted from all directions, blah, blah, blah. Okay, so everybody knows about that, okay? So he invented practically what we call barometers, so he actually established the existence of air pressure, liquid pressure here. Torricelli is famous as a physicist. And he also solved this problem. The problem is the following. The problem that Pharma proposed and himself couldn't solve. It's the following problem. At which point is, okay, so for every point that you take inside the triangle ABC, you can, of course, take the distances AX and BX and CX, okay? And the question of Pharma was the following. Where should I choose the point X so that the sum of these three lengths is a minimum? That such a minimum exists is clear to you because you have done basic calculus, basic analysis. The set of points inside this triangle ABC, including the sides, is a closed set. It's also a bounded set, so it's a compact set. The sum of these three lengths is a continuous function of the point X. So a continuous function, and it's a positive function. Okay, it's always positive. So it must have a minimum somewhere, at least at one point. So where does that occur? Well, if you try to do it with calculus, you will get impossible results. With calculus, you can do nothing, but with elementary geometry, you can actually, okay, so how to choose? So the question is how to choose. How to choose X inside ABC so as to minimize. Buraya yazmasaydık keşke. Okay, how to choose. Okay, if you like, where to choose X inside ABC so as to make the sum of the distances AX plus BX plus CX so as to make, as small as possible. Minimum. Now, where should it be? Now I shall show you. I shall show you where that point is, and the point is now become famous as the Torricelli point of the triangle. In fact, you will remember my talk about the remarkable points. So the Torricelli point, I'm going to show you in a minute where it is. The Torricelli point is also a remarkable point of the triangle. Well, I don't know how remarkable. You will decide about it yourself. Okay. In fact, this problem has also been called, well, in all my classes, I've called it. People loved it. People found it very funny. So why should I deprive you of the humorous side of it? This thing has been called also the problem of three lovers. Okay. So you're very popular with ladies. Okay, and you have got three ladies. Okay, A, B, and C, okay, with whom you have affairs simultaneously. And you are of course a sort of judicious sort of lover, so you don't have favorites. So you visit each lady equal number of times, okay? So the question is, where should you live so as to make the cost of your oil consumption, your petrol consumption to be minimum? This, by the way, is a very important logistic problem. It is rather important. Okay, so how to solve it? Well, actually, I've told you that the solution which I'm going to give you requires a certain restriction on the triangle that comes later, is a minimum. Okay, so what Torricelli does is the following. It's a little. So what he does is he constructs a equilateral triangle on the outside of the triangle ABC, with one side coinciding with BC. That is just if you like. He takes a rotation with center C and through angle 60 degrees, so that the point B actually moves into somewhere here. Okay, so let me call that point P. Okay, so that this, of course, the triangle BPC. Okay. So since this is 60 degrees, since this side is equal to this side, and since this is 60 degrees, BPC is an equilateral triangle. Okay? So you take, so the solution of Torricelli is important to take a rotation with center C and angle pi over 3, which of course sends B into the point P. Okay? Right. Now, let's go on and let's see what sort of an effect it has got on the point X. It rotates the point X, okay, and it occupies a position, let's say Y. Okay, so let's say the point X moves into Y. X is at the moment an arbitrary point. It's sort of test point. So that means, of course, you have got once again yet another equilateral triangle, like this. Okay. Good. So. Okay, I've got such a problem drawing equilateral triangles, It's when you're sitting so close to the blackboard, you tend to see things a little distorted. Right, there it is. Okay, so the rotation with center C through the angle pi over 3, sends x into y, b into p. Okay, so that means if you join y and p, then you have got two triangles. Okay, so it means C is fixed, of course. C is fixed, of course. It's the center of the rotation. So it means that, let's put all these things together. The triangle C, okay, so let me do it for you. The triangle CXB is rotated into the triangle CYP. So these two triangles are in fact the same, the very same triangles. They are congruent triangles, if you wish. Okay, and in particular, okay, so what do we have? So this length is, of course, AX. This length, XC, of course, becomes this length. That's the same, okay? So these two lengths are the same. And finally, the length XB, since the triangle CXB, okay, so this rotation, in fact, through this rotation, I know that the triangle CXB is in fact congruent to the triangle CYP. So it means that the line segment XB and the line segment YP, they are the same. So you see? Now we have got a curiosity. Well, you see, so we have found that the sum of the distances XA, XB, XC is in fact the length of the broken line that joins the point A, fixed point A, broken line, to yet another fixed point P. P is a fixed point in this geometry. A is the vertex of the triangle, it's there. And the sum of these three lengths has been broken down into the length of the broken line that joins A and P. So the question was, make this length as small as possible. How to find the minimum value? Now, of course, the obvious answer to this is that if x is the point at which this sort of thing achieves a minimum, then this must be the line, broken line. If it's, okay, so let me do it like this. If it's possible to draw a broken line from A, not a broken line, but a straight line from A to P, and if you can place the point X and Y meaningfully on it, then you have solved the problem. That would be the least part that would, at that point, the sum of the three distances will be minimum, it's as small as possible. So let me do it again. So let me draw the same triangle. Now that's a little creepy. I never can manage it, but I shall try. Okay, so that's the very same triangle. And now this case, in this time, okay, so that's the triangle, hopefully. And here is so let me rotate this about 60 degrees to obtain the point P. So that is the equilateral triangle, once again. And now, so that's A, and that's P, and that's the point B, that's the point C. So in search of the position of the point X, which makes the whole thing a minimum, I draw the straight line that joins A and P. Okay, so how do I erect this green equilateral triangle so as to find the point X? Well, that's quite easy. All you have to do is to draw a straight line through C, which makes angle 60 degrees. Okay, and 120 degrees with this line. Okay, so you have got here you have got the, okay, so that's, so this is it. Here we are. You're finished. Okay. This is the position. So the position that this point occur. Okay. So what's this point F? How do I obtain this point? Well, you can you see. Okay. So I've actually constructed this point AF. So Schrödinger theorem clearly. Schrödinger theorem clearly. The sum of the three distances AF plus BF plus CF being the length of the line segment joining A and P is definitely less than the sum of AX plus BX and plus CX, which is of course the length of the broken line that joins A to P in this fashion. So what's this point F? I found that this point F is on the line AP if P is the point which is obtained from the point B by a rotation of center C and through the angle pi over 3. In other words, if you construct an equilateral triangle, okay, with one side at BC outside the triangle ABC. Okay, but you see, this sort of construction would actually this should work with three other sides. You know, I've already told you, a triangle is a rather democratic thing. So the point F can be constructed as follows. What you do is you take your triangle A, B, C, and on each side you erect, so to speak, an equilateral triangle. Okay, like this, and let's call this P as we called. Let's call this Q, and let's call this R. So we know that the point F shall be on the line segment AP. It must, by the very same reasoning, also be on the straight line BQ, and it must also be on the straight line CR. So these three lines must have a common point. They must be concurrent, and that is okay. So let me make it absolutely clear that this is an equilateral triangle. This is an equilateral triangle, and this is an equilateral triangle. Okay, so things like this. Okay, so if you take these three lines, they must be concurrent, and the point they concur is called the point F, and it is referred to as the Torricelli point, actually. Torricelli point. Actually, many people call it the Pharma Torricelli point. So it really doesn't matter. It does matter because it's we know about this point because of the genius of Torricelli. But then again, Pharma is the person who proposed the problem. Right, şimdi çocuklar. There is one shortcoming. There is one shortcoming in this problem. If in order for this argument to work, you see, in order for this argument to work, actually, the angles of the triangle, all three angles of the triangle must be, so the angles A, angle B, and angle C, they must all be, okay, so let me express them as absolute values. They must all be strictly less than 120 degrees. And you see what happens. What happens is that, for instance, if the angle A, so if your triangle is a, how should I say, is a very flat triangle, okay, it's almost a splinter, let's say, so this angle is larger than 120 degrees. What happens is, of course, that the, okay, so for instance, if you erect an equilateral triangle in this part of the world, and if you erect an equilateral triangle in this part of the world, and if you try to construct the Pharma point, the Torricelli point, by joining each vertex to the opposite vertex of the equilateral triangle, so you get something like this. And okay, so this is quite obviously not wanted. That's ABC. This is your equilateral triangle. This is your equilateral triangle. And your Pharma point is, well, I need a little color. So your Torricelli point lies outside the triangle. Outside the triangle. So this won't do. So for instance, if the angle A exceeds 120 degrees, then the Pharma point, which is constructed in this fashion, will lie outside the triangle. So that's not admissible. In fact, I shall come back to this problem. If one of the angles exceeds 120 degrees, then the solution of the Fermat-Torricelli problem is that vertex. For instance, if your triangle is so flat that, so let's say the angle at the vertex A is larger than 120 degrees, then the solution which gives you the minimal oil consumption, so to speak, is the point A. So, I mean, in a sense, if you interpret it as the problem of three lovers, okay? So you have to marry the lady living in the city, in town A. Okay, so you have to live with her so as to make the oil consumption a minimal. Okay, so you live with her and you visit the others. Right. Okay, so that I shall do it later. I shall come back to that problem later. So this is the solution if none of the angles actually exceeds 120 degrees. Okay, so let's take a break. Let's take 10 minutes break.